Okay, so I think we can start. Welcome back. So last time we looked at adaptive control. We started looking at adaptive control. And so remember we had basically a pendulum with an actuator, so you could view this as a one-link robot. And we had three unknowns. The inertia of the system, A1, which was unknown but positive. The damping coefficient, A2, and A3, which was MGL. And we said, although M and L are both unknown, the only practical unknown from our point of view is MGL. So, and of course, we were still interested in a trajectory control problem. So the problem of making some tracking error go to 0. And this was a second order system, so we still used the idea that it's easier to deal with first order systems when you measure the full state. And so we introduced, as we had in the case of robust control, this intermediate variable, S equal x tilde dot plus lambda x, and to kind of belabor the point that this is a variable which contains the n-1th order derivative, we wrote it as x dot minus x dot r, where x dot r is just notation, which means everything else in S, okay, which happens to be this. And of course, here we picked a second order system because it had this nice physical interpretation, but using this intermediate variable and higher order versions of it, as we discussed, whatever we did would work with any system of nth order, right? Because it would just be x to the n minus xn to the r. Okay. So that would work in exactly the same way, and actually in the homework you'll play with a third order system. So what was the idea? Well, we started playing with reasonably simple choice of Lyapunov-like function, which was just S square. We noticed that if we used S square, we would have, when we differentiate V, we would have SS dot, so we'd have this J term appearing everywhere as the inverse of J. So just to simplify this, we put this J term here. This J term is unknown, but we do know it's positive because it's an inertia. And so if we differentiate V, and we won't redo the calculation, but we said that we would get S times U minus Y times A, where Y is a matrix which reflects what we know about the dynamic structure. So Y here was equal to x double dot R, and then x dot, absolute value of x dot, and sine x. And so if we pick U equal y a hat minus k times s, so this is basically like a PD term and k is a constant, positive constant, then this y a hat is trying to do its best to throw away this term ya, to compensate for this term ya, based on estimates of the unknown parameters a1, a2, a3. So this would give us minus ks squared plus sy a tilde, where remember a tilde was a hat minus a. So this term, of course, is something we like. It's a v dot negative, and also it's proportional to s squared. So if we use Barballa's lemma to show that v dot tends to 0. If we just had this term, it would mean that s tends to 0. So, but of course we have this term which we don't know the sign of. So the idea is to add to this Lyapunov function candidate, which is a quadratic term in the tracking error expressed in terms of our composite variable s, to add a quadratic term in the parameter estimation error. And then the parameter estimates are chosen so that when we add the corresponding term here, this whole quantity is 0. So we saw that this corresponded to adding this so-called adaptation law, y transpose s. Okay, so this is control, and this is adaptation. And so if we take the combination of this control law, which uses a hat, and this adaptation law, which is basically just chosen to make this red parenthesis be 0, okay, then we guarantee that v dot is going to indeed be equal to minus ks squared. All right, so the idea was to just add a quadratic term in the parameter estimation error to let, of course, this parameter estimation error be time varying, otherwise there's no way to get something from v dot, right? So it meant that a tilde was time varying, and therefore a had to be time varying. A hat had to be time varying. So we did this algebra, we got this extra term, and we basically just solved for this extra term to make the parenthesis equal to 0. And so this guarantees that v dot is equal to minus ks squared negative, which in turn, through Barballa's lemma, we'll come back to that in a second, implies that s tends to 0, and therefore that x tilde tends to 0. Okay, so that's where we were last time. Okay, so little remark about Barballa's lemma. Okay, so remember, Barballa says, you know, suppose you find a lower bounded v, a negative, such that v dot is always negative and such v double dot is bounded, then v dot tends to 0. Okay. And so that's what we used here, v dot tends to 0. So v dot tends to 0 implies that s tends to 0 because v dot is equal to minus ks squared. And s tends to 0 through this kind of implicit dynamic definition that is s implies that both x tilde and x tilde dot tend to 0. So by using this result, using Barballa's lemma, we show that v dot tends to 0, which implies that s tends to 0, which implies that both x tilde and x tilde dot tend to 0. So when we did that, we said that it's easy to check that v double dot is bounded. Okay, let's just detail this just a little. Okay, so you have to realize, of course, this conclusion from Barballa's lemma, as we said, is a pure result in functional analysis. Okay, there's a easier, more immediate conclusion we can get also from Barballa's lemma. If v is bounded and is lower bounded and v dot is always negative, right? It also means that v is bounded, is upper bounded as well, right? Because it starts at some value and it can only decrease, all right? So if you want the first part, if we wanted to add it, which is obvious from these two hypotheses, is that v itself is bounded, right? Right, because we start with some v, and v can only decrease. So we know it's lower bounded, and it's of course upper bounded by its initial value. Okay. All right. Now, as I said, often this, as I said when we talked about Barbell's lemma, right, this is often used to prove V double dot bounded. Right? So in other words, this, which is really a direct consequence of just the first two hypotheses, is often used to prove the third that the third hypothesis is verified, namely that V double dot is bounded. Okay. So a little more explicit here. Okay, so here we have an example of this. Okay, so V is 1/2 of JS squared plus 1/2 of A tilde dot, A tilde transpose P inverse A tilde. What's V double dot? Well, we've computed V dot, right? We don't need to redo this computation, right? So we have V dot, okay? So it's derivative of V dot, okay? And so it's minus 2ks S dot, right? So to show that V double dot is bounded, we just need to show that S is bounded and that S dot is bounded, right? So it's minus 2ks, and S dot is X double dot minus X double dot R. Okay. Now, we know that V is bounded. As we said, that's a fact from the first two hypotheses. But V is also a sum of squares, sum of two positive terms. So the fact it's bounded means each of the positive terms is bounded, right? J is a constant, P is a constant matrix, okay? So it means that S is bounded, and A tilde is bounded, and therefore A hat is bounded, okay? Because, and A hat is bounded, sorry, because A is constant. Right? V is a sum of squares. We know it's bounded, so it means that both S and A tilde are bounded, and since A is constant, it means both S and A hat is bounded. Okay? So it shows immediately that this term is bounded, S, right? And then, of course, if you compute X double dot, you just plug it back the whole dynamics, and now every single term in the whole dynamic is going to be bounded because S is, right? Remember that the fact that S is bounded implies that X tilde and X tilde dot are bounded. And since we assumed the desired trajectory was bounded, right, and its derivative, then it means that X and X dot are bounded. Okay, so in other words, we won't do this every time. We said, you know, it's a technical condition which has to be verified, okay, and typically it's the way it's done. It's really a consequence of the fact that V is bounded and the structure of V. Okay. So you compute V double dot and you check that all the terms that show up, you know, are bounded. You still have to do this, right? Because suppose you had a 1 over X somewhere, right? Then it might not work, right? So you still have to check that. Okay. But that's a technical thing that you just make sure is correct. So that's why I didn't go through that last time, because it's not the main story, but you still have to do that. Okay, questions about that? Yes?
I missed that part. How did we see that S is bounded, just the fact that it goes to 0?
Oh, no. V, right, V is bounded, we agree? Because, okay, and it's a sum of, and V is the sum of two positive things, so it means that each of the positive things is bounded. So S square is bounded and A tilde square is bounded. So again, you know, this is a technical point to verify that V double dot is bounded. You know, basically something that you check. Okay, the subtlety in all of these things is generally to design V and V dot and the adaptation law and so on so that it works. Okay, but still you have to verify this. Okay. Questions about that? All right. So here you see we used both Barbella's lemma and this notion of S, okay, this notion of this composite variable which itself represents an implicit dynamic so as to replace an nth order problem, in this case a second order problem, by a first order problem. Okay? Questions about that? All right. So we also made a remark, I won't come back to that. We also made a remark on sufficient richness. We said that this did not necessarily imply that the parameters converge and that to very exact values, and the reason was that what we had was js dot plus ks equaled y times a tilde. So what converges to 0 is y times a tilde, but not necessarily a tilde. And then we gave conditions on the desired trajectory on how complicated the task is to automatically imply that the parameters converge. Okay? So we said adaptation is done on a need-to-know basis, just like in a spy movie, right? And it's a feature, right? Because it estimates parameters just well enough so as to get the system to converge to the desired trajectory. If the trajectory is so challenging, so rich, that there's no way to converge to it unless you estimate the parameters exactly, then, of course, it will estimate the parameters exactly. And last time we gave an equation to quantify what we meant by rich in terms of its trajectory. It meant that on average, the matrix Y transpose Y computed along the desired state was positive definite on average. Okay. So basically, this is not very precise, but we made it more precise last time. Okay, questions about that? So it's the desired trajectory is sufficiently rich, and therefore the parameters converge to their exact value if this matrix YD transpose YD, which instantaneously can only be, in this case, of rank 1, on average, on time average, covers a three-dimensional space. Okay. Questions? All right, so let's go one step further. Let's take the same system, or let's start, if you want, with the same equations, and say, well, you know, instead of this being equal to u, let's make it equal to some dynamics f of x, x dot, and t plus u. The idea being, you know, you could start with a system and you could add some extra forces to it. So these extra forces would be in this form of f of x, x dot, and t. Or perhaps you've said, well, you know, this system was supposed to be on the water and this was the square drag term. This was really a very poor model of this, what's happening on the water, so I'm going to add this term, okay? But this term I may not know very well, okay? So in other words, you have, again, the same story as in pure robust control. In other words, you have an estimate of this term, and the estimate minus the real thing is bounded by something known, which we'll call capital F. Right? And of course, the reason why we did the adaptive control thing before is that if this F is 0, then we have perfect tracking, okay? While if we just considered these terms as unknown but bounded, first we would have to know the bounds, and then of course we would not have perfect tracking, okay? So in the pure adaptive control case, we explicitly use the fact that the unknown dynamics was just described by unknown constants to basically get rid of the effect of these unknown constants. Okay? So here we go one step further. We say, okay, so we have the whole dynamics. Some of it is described in terms of unknown constants. And some of it is described, just as in robust control, in terms of an estimate, which is somewhat far, which can be a certain distance from the real thing. And we know just how bad this distance can be. All right? So the question is, how do we do adaptive control on this? And remember, we defined loosely adaptive control as saying we're trying to make the system behave as if the unknown constants were known. Right? The unknown constants appearing in the dynamics were known. Okay? So if the unknown constants appearing in the dynamics, which are still the same, right, which are still A1, A2, A3, if these unknown constants appearing in dynamics were known, it means we would have to deal only with this F term, right? And so basically we would have exactly what we saw in robust control, right, except applied only to this residual term, which is not described by a known constant. Okay? So that's what we're trying to do now, right? We're saying we have a dynamics, it's unknown. Some of the uncertainty is in terms of unknown constants, masses and so on, right? Some of the uncertainty is just estimated, and then we have a bound. Okay. So, now, you know, as I said in math, you have to be lazy, but not too lazy in the sense you have to have realistic assumptions. Okay. So, in this case, what should we hope to achieve? Well, what we should hope to achieve is that the system behaves as if the unknown constants were known. But still, of course, we do nothing more about this term than we would do in robust control. Right? We haven't done anything new about robust control. Right? So we want the system to behave, at least after some transients, as if A is known, i.e. as if we only had to be robust to F. So to make this a little more explicit, so first of all, what could we say? Well, you know, it means that, you know, we're going to say, well, if we wanted to just to be robust to F, we would have a boundary layer, and we would know we would tend towards this boundary layer, and by tending to this boundary layer, we would know certain bound on our original tracking error X tilde. All right? So instead of saying our goal is to tend to the same boundary layer as if we add F alone, we're going to say something equivalent, that we're just going to create a notation. Okay? And this notation we're going to call S delta. So we're going to define a variable S delta such that S delta is less than some phi, meaning if we have a boundary layer of width phi, we are in there. Sorry, S is less than some phi, sorry. Define variable S delta such that if S is less than some phi, in other words, if we have a boundary layer of width phi, we happen to be in the boundary layer, we're going to define this variable such that S delta is 0. All right? This is just to say, well, what we're trying to do is tend to this boundary layer, okay? So tend towards this inequality, and we're going to replace the notion of tending towards this inequality to tending to this variable being 0. Okay? So how do we do that? Well, there's many ways to do that, but it's very easy, right? What we can just do is put a dead zone in the definition of S between phi and minus phi. And so if we look at the variables S delta, which is basically just parallel to S, right? So this is the variable S, if you want. So if we look at this variable S delta, which is just parallel to S, but we have a dead zone in here, right? So when S is between phi and minus phi, then S delta is 0. and that's the only place where it's 0, so this is verified. Okay, and of course, I mean, we could round the corners if we wanted and so on. The main thing is that we have this dead zone, right? And that's the only place where S delta is 0. Okay? So I'll let you verify. It's very easy to check, right? That if you're trying to get the formula for S delta, you'll get S minus phi sat of S over phi. And that's easy to check, right? Because when S is larger than phi, this is simply S minus phi. Right? And when S is smaller than minus phi, this is S plus phi. And inside it's 0. Okay, so it's easy to check that S minus phi times sat of S over phi is exactly what I drew in orange. Okay, everybody sees that again? When S is larger than phi, this line is simply S minus phi. When S is smaller than minus phi, this line is simply S plus phi, minus minus phi, right? And in between sat of S over phi is S over phi, so you have S minus phi S over phi, so that's 0. Okay? And it's continuous. All right. So what have we done? We've just created a variable such that the notion of tending towards a specific boundary layer with specific width is equivalent to having this variable being 0. Okay. All right. So now what are we going to do? So we're trying to design a controller, probably with some kind of adaptation law, which makes the system converge to a boundary layer specified of width phi, presumably specified corresponding to only this error capital F. For simplicity, this is, you could do the same thing in general. Just for simplicity here, we're just going to assume that this bound is constant. Okay? It's just not to carry around phi dots everywhere, but you can do the same thing otherwise. So we have this constant bound, and therefore, if you remember, we had this equation defining phi dot. If we have a constant bound, we can pick a constant phi. Okay. So what is a reasonable choice or plausible choice for V now? Guess, let's say, okay, because something to try. Yeah?
So F constant is, do you mean over all x and?
Yes, it doesn't depend on x and t. It's just to avoid. You remember we said you can pick a constant phi, but it's better to pick a time-varying phi because f is time-varying, capital F is time-varying. So if f is constant, you can get away with constant phi, and so you don't need to carry around phi dots, things like that. This is just to get the idea. Okay, so what's a reasonable choice of V? Well, you can think a little about it, but basically, instead of 1/2 of js square, we can pick 1/2 of js delta square and see what happens. Okay. Now, it's very easy to verify because we'll need this when we differentiate S delta square. Incidentally, S delta is not differentiable here, but S delta square is, right? Has rounder corners. So, right, the slope, right, of S delta is discontinuous, but the slope of S delta square is fine. So it's very easy to verify that the time derivative of S delta square is S delta times S dot. All right? So why is that? Because it's true here, it's true there, it's true in the middle, and it's continuous at the corners. Okay? Right? So So that's very easy to check, right? You can't put S delta dot because S delta dot is not defined at these corner points, but you can write S delta S dot. Okay. So if we differentiate this, therefore we get S delta J S dot, right? And so we're not going to redo this whole calculation. It would be a little tedious. So, but we're going to just see how it would change. So what's a control law now? Well, a control law would be, we could use y hat minus ks, by the way, but just to be more strictly tailored to this robust design, we can use minus k sat of S over phi as we would in a pure control, in a pure robust control law, right? If we had minus ks, it would be a term bigger in absolute value, so it would work too, but it would push things faster to the boundary layer. So let's try this control law. So what is it? It's y times a hat, as we would do in adaptive control. But minus k sat of S over phi, and sorry, I forgot one main term, of course. What should I add? Well, I should add minus f hat, right? Because if I just had f, right, I would do that, right? So the robust control term would be this, right? And then we have this extra term, presumably to handle the adaptive terms, right? So we're going to have y a hat to cancel the terms in A as before, minus f hat to cancel the term in F as best as we can, and then this term minus k sat of S over phi. All right? So can somebody see how this is going to change? So Js dot is equal to J x double dot minus x double dot R, right? So what changes in x double dot? Well, two things have changed. One is that, well, three really, but so one is that we're using a slightly different control law. And then, of course, that we're using S delta. So we have S delta times minus k sat of S over phi plus y a tilde, and then plus f of xt minus f hat of xt. So I'll let you, if you want, check this calculation. It's to be compared to this, okay, S times u minus ya, okay. So now the u minus ya gives you ya tilde, and then you have this extra term f minus f hat. Okay, so I'll let you check that, but it's very easy. All right. So this term, how can we write this term? S delta times minus k sat of S over phi. Okay, how can we write it a little more simply? Well, sat of S over phi is 0 when S delta is 0, yes?
One question, the second line is V dot, right?
Yes, so thank you very much. Yes, of course. Yes. So how V dot using this equation, of course. Thank you. So what's S delta times sat of S over phi? Well, remember S delta looks like this, right? So, and the saturation function is something which is maybe it's not worth drawing over this, right? The saturation function is something which interpolates between minus phi and phi, right? So, S delta sine of S over phi, sine of S over phi, sorry, S delta times sine of S over phi is really the same thing as S delta sine of S, because when sine of S over phi is anything other than sine, S delta is 0, right? We could redraw the saturation function up there, but feel free to do that, okay? And so what's S delta sine of S? It's simply absolute value S delta, right? So what we have is minus k absolute value S delta. Then we have plus S delta y a tilde. So let's leave it there for the moment. Okay, that's fine. Then we have this term, f minus f hat, okay, which is multiplied by S delta, so it gives us S delta times f minus f hat. Okay, and that's it. Okay, everybody follows this? So then, of course, we can play the same game, right? We're going to say, well, with this term that we don't like, and there's this term that we don't like. So this term, presumably, we'll deal it from a robust control point of view. This term, presumably, we're going to deal with it from an adaptive control point of view. So we're going to add the same quadratic error term here, which is going to give us the same extra term here, which we add here. And so what's the adaptation law to get rid of this, okay, to make this plus this add up to 0? Well, before, it's exactly the same thing, right? We had SYA tilde, and we were canceling this term with that, okay? Now we have a S delta YA tilde, and we're canceling this term with the same term, okay? So we're going to get the same equation, except we're going to get this S delta, right, in this equation instead of S. Right? We could redo the algebra if you want, but it's the same algebra. Before we had SYA tilde plus this red term, right, which had to be 0. Now we have S delta YA tilde plus this red term that has to be 0. So S has been replaced by S delta. That's it. Okay. So this is the adaptation law. Okay. And so what can we say? Well, we have V dot, which is equal to minus K S delta plus S delta F hat minus F, or F minus F hats. All right? Now, suppose I pick K, as I would in robust control, as F plus eta, right? Where F, capital F, is the bound on the error, not on the entire dynamics, but on these residual terms now, which are small f. Right? So a much smaller bound than we would have if we'd had bound on everything. All right? Suppose I pick this. Then what can I say? Well, I have that this term here is negative, right? And this term here is whatever it is, but in absolute value is less than this term, right? Because k is larger than capital F. So what do we have here? What's left here? Remember k is F plus eta, right? So in absolute value, it bounds this term, right? So V dot is simply less than eta S delta, right? K is F plus eta. Okay, if we want, we can write this more explicitly, right? So minus K, which is F plus eta S delta plus S delta F hat minus F. We see that this term is always of the correct sign and overpowers this term, and the only thing that's left is minus eta S delta. Right? Everybody understands this? It's always the same story, right? We have a term whose sign we like, and we want to make sure it's larger in absolute value of the term whose sign we don't know. Okay. All right. So we have this. And of course, minus S delta is negative. If you use Barballa's lemma, so the small technicality here, you need to, instead of saying V double dot bounded, you have to state a slightly more general condition, which says that V dot is uniformly continuous, but it still works in the same way. If we use Barballa's lemma, we find that V dot tends to 0. Okay. Again, V positive, V dot negative. Here, V dot uniformly continuous, which is a slightly more general condition than V double dot bounded. So we find that V dot tends to 0. But you see here, we had V dot tends to 0 implies S tends to 0 because V dot was equal to minus Ks squared, right? But V dot is not equal to minus eta S delta. It's less than. Is that a problem? We'd like to conclude that S delta is 0, tends to 0, right? But here it was very easy because V dot was minus K squared, so V dot was S squared, right? So V dot tends to 0 means S squared tends to 0, right? So here we have V dot less than minus what we want to tend to 0. However, well, V dot tends to 0, right? So this term is squeezed between 0 and 0, right? Right? So S delta tends to 0, right? Right, we know that V dot tends to 0. And we have 0 here, so it's fine. V dot is not equal to minus S delta, but it's fine. S delta is squeezed between the two. All right? So, what does it mean? It means that we took our original uncertainty, we partitioned it in two. One uncertainty which depends only on constant parameters. Two, the rest. We bounded the rest, which of course gave us a much, much smaller bound than if we had to bound everything. Okay, we bounded the error on the rest. And then we applied a robust controller where we cancel for our best estimate of this residual term. We cancel for our best estimate of the parameters, of the role of the constant parameters. We add a stabilizing term. We add an adaptation law. And we end up with S delta tends to 0. In other words, the system tends towards the same boundary layer that you would have if you had to deal only with little f. So we have exactly achieved what we wanted to do, namely have the system behave as if the unknown constants were known. Right? We tend towards the same thing we would have if these constants were known, a hat equal a all the time. Okay? So we tend towards the same boundary layer as we would have if the unknown constants were known. Okay? And therefore, the same residual error having to do with the width of phi and so on. Okay? So now, if we look at, so this is fairly clear what it does, right? It cancels the estimated dynamics for the whole system, the residual term and this part of the system due to only the unknown constants. This is a robustifying term. What's the interpretation of having this S delta instead of S in the adaptation law? Right? Before we had minus P y transpose S. Right now we have minus P y transpose S delta. Right? Where S delta again is this gadget. Right? Why does it make sense? Of course, I mean that's what the algebra tells us. Okay, but you know it's always good to sit and think from the point of view of the computer, right? Or wondering, you know, does this make sense, right? So why does this make sense? So what would happen if we had S here? Exactly, right? In a sense, this S delta is like is a matter of consistency, right? We've said we want the system to behave as if the unknown constants were known. So what would it do then? It would tend toward the boundary layer. Therefore, once you're in the boundary layer, maybe you have uncertainty on, maybe the A hat is not equal to A, but maybe also the whole reason you are in the boundary layer and not exactly on S equals 0 is because of these small f terms, the residual terms, right? You don't know which. If you had exactly estimated the parameters and then stopped them, these are the parameters, the only thing you could guarantee would be you are in the boundary layer, right? So it's a matter of consistency. It's just you don't know whether, what is this residual error being in the boundary layer due to? Is it due just to the things you're trying to be robust to, or is it due to parameter estimation error, or both? And therefore, this says, well, you know, wait and see. It says, in the boundary layer, I'm going to just stop adaptation. Perhaps temporarily, maybe I'll get out of this boundary layer here, right? Because there's also this adaptation going on, right? In this boundary layer, I don't know which is which. I'm going to stop adaptation, right? Keep the parameters constant, okay, until and if I get out of the boundary layer. So for those of you who've looked a little at machine learning, it's something very similar in spirit to what's called overfitting. Okay, overfitting is the case where you're trying to, you know, learn a model, learn a system, and you're getting better and better at it, and at some point you start getting worse and worse. And you have that also when you learn playing tennis or whatever, or playing the piano. You have to know what is the right moment to stop, okay? And the reason is pretty much the same story, is that at some point you're getting better and better because you're extracting more and more information and getting a better model and so on. And then at some point the error you see has nothing to do with the parameters you're trying to change. And then you're getting worse and worse, right? Because you keep tuning these parameters on irrelevant information, okay? So that's what this is avoiding. Okay? So that's the story here. Questions about that? Questions? All right. So now we know, again, you know, if it was a JX triple dot, it would be exactly the same thing because you define S and then the algebra is the same. So we know how to deal with adaptation for n-order systems in this form, where you have uncertainty due to unknown but constant parameters, and then the rest. Okay. So what we're going to do now is try to go yet one step further. Okay. It could still be the same system when we started saying, well, you know, everything is unknown but bounded. Okay. And then we say, oh, by the way, you have masses and so on, so we can be more precise. So here we're going to still try to exploit more information on the system if available. And that's going to be something we're going to write here. Let's see what time. First of all, any questions on that? No. Okay, so it may be just we're looking at different classes of systems, or it can be one system, but we making our model, and more precisely our analysis of model uncertainty, more and more careful and specific in the source of uncertainties. Okay? So suppose we're considering again something very the same kind of system. So before here we had f of x dot and t, right? So here I'm going to do something which may sound a little weird at the beginning, but suppose that we know that this f of x dot and t is really the sum of two terms, one which depends only, let's say, on velocity, phi of x dot, plus another term, g of x dot and t, right, plus u. Right, so we're getting more precise about this residual term. Instead of saying it has an estimate that is bounded, the estimation error is bounded, we're saying this residual term, f, if you want, is really phi plus g. Let's call it big, no, that's fine. Let's call it phi plus g, right? And this term here is a function only of velocity. And similarly, I could say it's a function only of position, or maybe I could say it's a function only of position and velocity, but not of time. Okay, there's lots of variation. But let's say it's a function only on velocity. So you see, here you have put a little more information about your system. You've said in this residual term small f, it's really something which depends only on velocity plus something else, right? And the something else, again, then we can bound as g hat minus g is less than some f. Let's call it f sub g, right? And this f sub g is this f sub g, of course, is smaller than the previous f, right? Because we've extracted this term here. Now, the slightly surprising result is that if we do that, if we know this, actually we can make the system pretty much behave as if we knew J, we knew B, we knew MGL, and we knew phi. Right? The simple fact of saying phi depends only on x dot, I would say on x either, actually is going to allow us to do that, at the price of just a little more computation. Okay. Now that may sound a little strange, so let me explain why I'm saying this. Well, so what do we have? We have an unknown function. Maybe we want to add a few smoothness conditions on the function and so on, but basically an unknown function. So before, in this matrix Y up there, second line, right, we had these kind of physical basis functions, sine x, x dot square with the right sign, x double dot r. Okay? We had these physical basis functions, okay, which we used to write y times a hat, which reflected what we knew about the structure of the dynamics. Okay? We had these physical basis functions, these physical multipliers, if you want, each multiplied by these numbers. Okay. Now, if I give you a completely arbitrary function, again, perhaps with some kind of smoothness assumption, even if you don't know anything about the physics of it, you can always, if you want, think about a mathematical expansion of this function. Okay? So I'll put any in quote because, of course, there's one could take a whole graduate course on just these mathematical expansions. Okay? But if you write phi of x dot, right, it could be really written as some infinite sum of coefficients, let's call them alpha I, and then basis functions, let's call them perhaps rho I of x dot. Right? If you take functions in general, you can write expansions of these functions, okay? You have to pick the right class of expansion depending on the class of function, but basically you can do this, okay? Now, you've seen this in a different context, right? Suppose we knew phi of this term was not phi of x dot, it was phi of t, but it was periodic in time, right? Suppose you think of this, you replace it by some function which is periodic in time plus the rest. Okay, what could we do? Well, we could do a Fourier series, right? We could say, well, this function is equal to a Fourier series where we know the period. Okay? And then again, the Fourier series is a bunch of terms, sines, omega t, and so on, multiplied by unknown coefficients here. Okay, because if we only know the function is periodic of period 17. Okay? So here's the same thing. We know we have this function and we can write it as a tensor basis function. Similarly, C periodic of period t, right? Could write a Fourier series. Okay. So you see, in a sense, what it's saying is that to the physical basis functions we have, the three physical basis functions we have, we can, in principle, add mathematical basis functions, much, much larger number, actually, strictly speaking, infinite. Okay. And if we do that, of course, these basis functions, of course, are known, right? The same way that the y's were known. So if we do that, in principle, we can do exactly the same thing, except we'll have a parameter vector set which will be much, much bigger, right? It will contain the original 3 plus all these alpha i's. Okay? But it's just saying, you know, once you've exhausted all your knowledge of physics, there's still math which can come to the rescue. Okay? Except, you know, it does it in a, you know, computational way. Right? Now, then, of course, as I said, you could take a whole graduate course on these expansions. So what is a good expansion? Okay, so desirable, some desirable, doesn't mean you need to have them all, right? But desirable properties of the expansions. So I've written it as a function of x dot, right? So at any x dot, only a few terms are needed for a reasonable approximation. Of course, all these terms can be quantified, okay? So, in other words, at any point x dot, you have this infinite expansion. But if you've done your job at function approximation and so on, pick the right basis functions and so on, this infinite expansion should be pretty close to just a finite set of terms plus a residual. Okay? So, how can you do this, for instance? You could have rho I of x dot is equal to, what's lambda rho a, no, not eta. It's like c of x dot minus x dot I for a bunch of specific velocities x dot I. and xi local, meaning it would look something like this. So, first properties you may want to have, in this infinite expansion, you want to be able to compute this infinite expansion as a few terms plus a residual, which of course you don't compute by definition. So one way to do this is to have these, each of these rho I of x dot to be really the same function just shifted, right? Rho I xi of x dot minus 1, xi of x dot minus 2, or whatever you pick for the x dot I. Right? So it's just a bunch of functions shifted. And then xi local, in other words, it's 0 outside of a certain region. Right? You see, if you do these two things, it means at any point you look around you, and only a few of these terms are not 0. Right? Because you've covered your system with these local basis functions, okay, at discrete points. And of course, at any point where you are, only a few of them are not 0. Okay? Again, you know, we could spend hours just getting into details of that. It's just to give you just the idea, okay? So one desirable property of an expansion would be this, would be that any instant you need to compute a few of these basis functions only, and therefore you need to update a few of these estimates only also, okay? So continuing on this, right? So at any instant, only a small, well, finite, ideally small set of Si is updated. So it doesn't have to be small, but certainly it has to be finite. So linked to this, the second desirable property, so this was 1, okay, 2 could be this infinite sum, which is the expansion, at any point we want it to be equal to this finite sum of, let's say, n terms. Plus the residual. Okay, so that's what I said before. At any point, this infinite sum we approximate as a finite set of terms plus a residual. But now I want to add an extra condition, is that I want the absolute value of this residual to tend to 0 fast as n increases. Right? I don't want this to take forever, right, in terms of convergence rate, right? So if I'm good at choosing basis functions, if I'm good at function approximation, then I should be able to do that. You see, in a sense, you know, if we wanted to use grandiose terms, right, it's kind of bridging signal processing and control, right? Saying how can you use tools from signal processing, from function approximation, and use them directly in the context of control, okay? Well, you can do that by approximating the dynamics. Okay. So this infinite sum at any x dot you want to write as a finite sum, as we said, and the residual term you'd like to go down fast as you increase the number of terms you keep. Okay, so that's a second property. Again, we don't have to have all of those, right? But these are often desirable properties. The third properties, which could be useful, would be to have orthonormal basis functions, rho I, Orthonormal, by the way, in the sense of the dot product between functions, all right? So this has to be what's called delta ij. So in other words, it has to be 1 if rho I equal rho j, and 0 if rho I is not equal to rho j. So it means the dot product of these basis functions is 0 between any two distinct basis function, and we normalize it at 1 otherwise. Okay. And as you can see, there can be a whole technology built on just generating basis functions to verify these properties. Okay. So why do we want them to be orthonormal? Well, it's just conceptually, if you want. Suppose that you look at the difference between the infinite sum and the finite sum. And let's take the norm of this, right? The norm in terms of this dot product. It's a function. Okay. Suppose you take two vectors in a finite dimensional space. Okay. You have coordinates of these vectors in an orthonormal basis. Okay. If you do the norm, the square norm of these vectors, the square norm of the difference, what are you going to get? Well, you're simply going to get the sum of the squares of the differences of the individual coefficients, right? Right? Suppose you take two vectors in a high-dimensional space. Okay. You have them on an orthonormal basis function. You look at the difference of these two vectors. You take the norm. You'll find the sum of the coefficients of these vectors square, because that's the basis function is orthonormal, right? So the infinite sum is the correct thing, right? This is the finite sum, where a number of terms in the infinite sum have been put to 0. Okay? So this term is simply the residual term times alpha I square, right? The sum over the residual term of the alpha I squares. Right? The infinite has all the alpha i's. The finite has some of the alpha i's. The difference square of the norm is just the sum of the alpha I squares. Just in the finite dimensional space. Here you are in the infinite Hilbert space, but it's just in the finite dimensional space. Okay? So, everybody understands this, right? You have a vector with lots of things, lots of terms, and you have a vector which has less. If you take the dot product, take the difference, you're left with the sum of the residual terms squared, the residual coefficient squared, okay? Because you have orthonormal basis functions. If that wasn't the case, you would have all sorts of cross products. So why am I saying this may be interesting, okay? Because suppose that you have to approximate a function, okay, and you've decided to approximate it with 400 terms, okay? And somebody says, wait a minute, budget restrictions, or the House hasn't voted, or whatever. And so now you're not allowed 400 terms, you're allowed 27. Question is, which one would you pick? And this says, what does this say? Which one would you pick? You have your expansion. You've worked hard to have your expansion on the 400. And so somebody says, wait a minute, I can't take the 400. I want you to choose your best 27. What are your best 27? they're going to be the ones with the largest coefficients, right? Because each time you throw away a term, you put its square in there. So the best ones, the ones you want to least throw away, are the ones with the largest coefficients. So out of your 400, otherwise, if you didn't have an orthonormal basis function, you would have to pick all the combination of the 27 and these 400, It would take a while. But here it says, no, you just pick the 27 largest. Okay, so that's the power of the normal basis functions. Okay, and so that's why in an expansion it may be a useful thing to have. Okay, and again, you can spend the whole graduate course deriving a technology to do all of these things well. Okay, but you can also already use simple versions of it, with something called radial basis functions, which are basically, extensions of Gaussians. So of course, it could be also multidimensional. In other words, you could have a function of x and x dot. You might say, well, why don't I just treat the whole f of x dot and t as just one thing to approximate, okay? You could, but the problem with t is that it goes only in one direction, so you never learn about future t, right, by where you've been. So unless you know something temporal about the function, like it's periodic, okay, you're going to do this on the state part, not on the t part. Okay. So, for instance, Gaussians, there's a whole beautiful theory developed in the last 20 years of basis functions which are local in both space and frequency, that's wavelets. And those of you who look at courses on wavelets, you'll find out, that you really build numerical algorithms to obtain these kinds of properties. Okay. And in a sense, wavelets were derived by mathematicians, and maybe 40 years ago it would have been strange to derive things as saying, well, I'm going to build a nice lookup table which is going to tell you what are the right basis functions. Okay. You would have liked to have maybe something more explicit, more analytic, okay, to do that. But of course, on a computer, when you call sine x or cosine x, you're actually calling a lookup table, okay, because the computer doesn't know what sine x is, okay. So it's just building the lookup table that will fit your best approximation desires, right? So so it's a very beautiful set of mathematical tools that can be developed that way. So, right. So you see we've gone in steps, right? We started with robust control. Then we said what would happen if all the uncertainty is due purely to unknown constant. Then we mixed the two. Okay, that was up there. And then we said, well, we can go even further, because if we know that part of this residual uncertainty is a function only on position or velocity or both, okay, then we can augment our basis function, our y matrix, if you want, with a new set of basis function, in principle infinite, but in practice such that at any instant we handle only a few basis functions and a few coefficients. So if you want to have a large memory for all these coefficients, but at any instant you do only a few computations. Okay. And then we can do exactly the same thing as we did before, okay, as we did in this robust control case, but in the case of this expansion in terms of mathematical basis functions. Okay? And where does the fact that we have a residual go? Well, it goes exactly where the capital F used to go, right? It just adds to the capital F, right? Except, or here to the capital FG, right? So basically, we expand this, we do our best to approximate this, And whatever is left over will be just added to capital FG. This will be this residual term. So in a sense, you even have an explicit trade-off, between how much can you do computationally online, how many terms are you capable of computing online in real time, and what kind of precision you get, right? Because the more terms you get, the smaller this numerical residual term will be, and therefore the better your precision will be. Okay? But in practice, it works very nicely to just have a few terms. If you have to deal with stiction or something like that with a few Gaussians, you do much better than without them. So that's kind of the general story. Any questions about that? Good. So what we'll do next time is we're going to look at one set of application example, which is robotics, okay? And we'll start from the beginning. We're going to take a rigid manipulator and start wondering, how can we control it in position? How can we control it in trajectory? How can we control it adaptively? Okay, so that's what